Well, here we are at Lecture 5C, so the third part of Lecture 5, and we are going to be talking about enthalpy and calorimetry. So calorimetry is really the measuring of heat. More specifically, we're looking at measuring the heat of reactions. So when we're measuring what the heat of a reaction is, there are some factors that we do have to take into account. Mainly, what does our reaction consist of? Does it have solutions and solids only? If that's the case, then we can generally use an open calorimeter. An open calorimeter would be something as simple as a styrofoam cup, something that keeps the heat in, but is open to the atmosphere, which allows that reaction to occur under a constant pressure environment. That constant pressure is generally atmospheric pressure. If we have a reaction that involves gases, obviously we don't want to use an open calorimeter because the gases would then leave and our reaction is no longer a closed system. So generally we use a different type of calorimeter, one that can contain the gases within a certain volume. And so we use something that is called a bomb calorimeter. And so we use that bomb calorimeter to contain the gases. And in those cases, we say that the reaction occurs under constant volume because gases may be evolved or used up. It's possible that the pressure inside that bomb calorimeter will change. However, the volume will remain the same. And here's just a simple picture of a bomb calorimeter. We see some of its various parts and pieces there. We have our bomb, which is this, large stainless steel vessel here. The walls of the bomb are generally very thick, centimeter and a half thick of stainless steel. Everything is stainless steel in here. You have your sample sitting down here. There's going to be a little wire that goes down and touches the sample to help ignite it. Inside the vessel is usually oxygen at pretty high pressures, somewhere around 10 to 15 atmospheres worth of pressure of oxygen to ensure complete combustion when the material does ignite. When it ignites, the heat from that reaction will come out. It will heat up the bomb, which will then heat up the water. The thermometer right here measures the change in the temperature of the water. The stirrer that's up here will help ensure that the water is the same temperature throughout so that the heat is evenly distributed throughout that water sample. And if you know how much water you have inside that overall calorimeter, which is the whole device here, if you know how much water is in there and you know the specific heat of the water and you know how much the temperature changed, you can determine how much heat came out of that sample. And if you know how much sample you had, you can determine a heat per gram or a heat per mole. So that's how we use a bomb calorimeter. Not something that we see a whole lot of, but it's just really cool. So I thought I'd go ahead and show that to you. So when we have constant volume calorimetry, such as what we have in a bomb calorimeter, you have no work taking place. You have to remember work is done by a change in volume due to pressure. And since you have a constant volume, change in volume is zero. So our delta V is zero. So P delta V is zero, which means that work is zero. Now what that does is it simplifies our calculation quite a bit because that means that all changes in energy come solely from the form of heat, a change in the amount of heat in that reaction. So we don't have to worry about W in our Q plus W. Now just some simple equations here. We do have to worry about what's the heat of the calorimeter. The calorimeter itself has a specific heat. Generally, it's very high. We don't want our calorimeter changing temperature, so usually it's a highly insulative material, but it doesn't matter. There's nothing that is perfectly insulating, and so it will change temperature just a little bit. So a calorimeter gets calibrated, and we can figure out how much heat was absorbed by the calorimeter itself. We know that overall the calorimeter with the water and everything is going to have an opposite heat change to that of the reaction. So all of the heat comes out of the reaction, goes into the calorimeter environment. So they have an opposite sign in terms of the amount of heat. And the delta E of reaction is just going to be the heat of that reaction. So just a lot of little manipulations there to get to a change in energy of the reaction. And again, that specific heat of the calorimeter is the heat capacity of that entire calorimeter and all of its components. So again, you generally calibrate that with a known substance where you know the heat of reaction and you can calculate what the specific heat of the calorimeter is. Now, if we look at enthalpy, enthalpy is a slightly different type of heat of reaction. So enthalpy is defined as the heat exchange in a reaction under constant pressure. And this is usually what we have when we have an open system. We use enthalpy a lot more often than we do the heat involved from a constant volume situation, because in a constant pressure situation is much easier to deal with. It's much easier to set up. Again, it's as simple as measuring the heat change in a solution in a styrofoam cup. So generally, we use enthalpy a lot more often than heat from a constant volume system. So again, open system for constant pressure. Enthalpy is an extensive property. Remember what that means. Intensive property is something that does not change with amount of material. An extensive property is something that does change with the amount of material. So hopefully this would make sense. A way of thinking about it is if I burn twice as much material, I'm going to get twice as much heat out of a particular reaction. So enthalpy is extensive, which again, dependent on amount. Enthalpy is a state function, which means it doesn't matter how we calculate or how we get from start to finish. Calculating our starting enthalpy and our finishing enthalpy, our change in enthalpy will be exactly the same. So it's not affected by the path that we use in order to calculate the enthalpy. So when we calculate the enthalpy of a reaction, we examine it strictly from the point of view of the system. That's pretty much how we view everything in thermodynamics in chemistry, is from the point of view of the system. So a reaction starts at the reactants, it finishes up as products, and so we always have that change in enthalpy, the enthalpy of the products minus the enthalpy of the reactants. We'll look at that here in just a little bit. Now, we do have a hard time calculating actual enthalpy. It is very difficult. So the enthalpy, the actual enthalpy of reactants and the actual enthalpy of the products is difficult. So for a reaction, the only thing we're really worried about is what is the change in the enthalpy. We don't necessarily worry about where we started and where we finished, just what was the difference between starting and finish, because any of the energy that goes out or goes in is energy that we can use to do work if it's coming out, or to know how much work or energy has to go into a system in order to make it happen. So let's look at this idea of delta H. So again, we can look at delta H. We can think of delta H as enthalpy of products minus enthalpy of reactants. We don't generally use that equation much. It's just kind of a philosophical equation. That's what the delta H really represents, is that difference in enthalpy between reactants and products. Now, remember we said that enthalpy is a state function, and that means that delta H is also a state function. And I've got some a label there that doesn't show up particularly well. I forgot to color it white. On the other end of that arrow, it says constant pressure. So that little Q, again, is heat, and the P there, that's a subscript of that Q, means constant pressure. So delta H is equal to the heat involved under constant pressure. So the change in enthalpy is equal to the amount of heat either absorbed or given off under constant pressure conditions. Another way of defining enthalpy is as the internal energy of the system plus the product of pressure and volume. So we can say that H is equal to E plus PV. Now again, we're not usually worried about the enthalpy itself, H. What we are normally worried about is the change in enthalpy. So we're looking at delta H. And so if we're looking at delta H, we can change the E to a delta E and the PV term as well. But since we're under constant pressure conditions, the P is not going to change. However, the V can. And so we have delta H is equal to delta E plus P delta V. Okay, we should recognize that P delta V, that's the amount of work that's either done onto or by the system. So that's the amount of energy that is involved in work. Now, most of the reactions that we tend to do, that we look at this level in chemistry, are done as solutions or in solution. And so there is virtually no work done because within a solution, the volume does not change. It pretty much stays exactly the same. So that delta V term is usually zero. The pressure doesn't matter if delta V is zero. And so what we're really looking at is that delta H is equal to delta E. So just kind of as a summary of all that we looked at with enthalpy, that value of delta H is the amount of heat absorbed or given off by a reaction under constant pressure conditions. Okay, and if the value of delta H is positive, that means that the system has absorbed energy from the surroundings. The system has gained energy, so that's why we say that delta H is positive, and we call that reaction endothermic. Okay, and vice versa, if the value of delta H calculated is negative, that means that the system has lost energy. It has given off energy to the surroundings, and in that case, the reaction is exothermic. We can also look at the thermochemical equations involved in changes in enthalpy. So these are our reactions where heat is either absorbed or given off. And because enthalpy is an extensive property, the amount of heat that's given off or absorbed is dependent on how much material is going into that reaction. So it also depends on how we write a reaction. So the same reaction can have a different delta H depending on how we balance that reaction. Let's look at a couple of examples here that are not showing up because they are colored out. I apologize for that. I will get that fixed. So let's look at the burning of ethanol here. If we have C2H5OH plus 3O2 going to 2CO2 plus 3H2O. Okay, so just burning of ethanol. That has a delta H of negative 1235 kilojoules. So as written, that reaction gives off 1235 kilojoules. So if that means if I burn 1 mole of ethanol and 3 moles of O2, I can expect that amount of heat. But what if I don't have 1 mole of C2H5OH? What if I only have 20 grams of it? How much heat can I expect to get? Well, I know if I have 1 mole, I'm going to get 1235 kilojoules of heat given off. So what I need to do is see how many moles is 20 grams. So for that, we use a molar mass of ethanol, and that turns out to be 46 grams. So I take my 20 grams, my 1 mole per 46 grams to convert to moles. My grams cancel out here, and I'm left with 0.435 moles of ethanol. And then I know that I get 0.435 moles of ethanol in my reaction. How much heat can I get? Well, I know that I get 1235 kilojoules of heat out for every 1 mole. So I just do the calculation so that my moles cancel, leaves me with kilojoules, and I get negative 537 kilojoules of energy if I use 20 grams rather. Now for constant pressure calorimetry, we do that a lot, like I mentioned, because a bomb calorimeter isn't always very practical. They take quite some time to set up, a lot of time to run, and lots of places to make errors. Sometimes you have to do them for different things, but a lot of times in the labs, especially at this level, we don't really use them. So instead, generally, we are using these calorimeters that are open to the atmosphere under constant pressure conditions. And so in these cases, what we can do is we can calculate the heat that's absorbed or lost by a solution using the equation that we learned earlier, where we have Q is equal to M times C times delta T, where the Q is that heat of the solution. That's going to be equal to the mass of the solution times the specific heat of the solution. And since it's generally an aqueous solution and it's mostly water, for that specific heat, we generally just use the specific heat of water. Just water versus the solution itself does not have an appreciable difference in the value of the specific heat. And then we just use the delta T as well. So once we do these, we can find the heat of the reaction using these relationships. We can figure out what the Q of the solution was by knowing the mass of the solution, the specific heat of the solution, and how much it changed its temperature. So that can allow us to calculate Q of solution. I just need to change the sign of the Q of solution to get the Q of the reaction. And the Q of the reaction is going to be equal to the delta H of the reaction. So we can actually do quite a few calculations here to reach the enthalpy of reaction for a reaction that's occurring in solution. Well, that finishes out this installation of our lecture 5. I will try to get those blanked out labels fixed and pasted into the video. But if you have any questions on any of this material, please make sure that you contact me.